Today, I will be giving a little background on high-resolution spectroscopy of molecular ions and their chemistry related to astrochemistry. But mostly, I'll be focusing on a story on this one interesting molecule of C3H2+ that I did, a project I was involved with Stefan Schlemmer's group at the University of Cologne, but during my PhD at the University of Illinois. So a little background as to why I've been interested in molecular ions and why people are as well. So it comes to this question of how can chemistry occur in the interstellar medium? So it is very cold. We're talking temperatures, down to tens of Kelvin, and the concentrations are very low. And so conventionally, with terrestrial chemistry, you would expect nothing really to happen, or these molecules would be destroyed faster than they can be created. So if we consider, let's consider the formation of water in the interstellar medium. So we could look at this neutral-neutral reaction between hydroxyl radical and hydrogen, which is exothermic, but it has this activation barrier, meaning that it basically will not occur in these environments. So this would take longer than the lifetime of the universe by far. But if we instead consider the reaction between an ion, so OH plus, and molecular hydrogen, this is now a barrierless process, meaning that this can happen at near the collisional rate. And so now we're talking about timescales on the orders of hundreds of days. So very, very fast for an astrochemist. And so this means that these processes can compete with the destruction processes and actually lead to some chemical complexity. And so you can put together these reaction networks, which heavily rely in the gas phase on ion neutral chemistry to explain some of the molecules that have been observed. It's very valuable in order to try and understand how well these molecules work, to confirm them with observations. And this is largely done through radio astronomy to detect different molecules or molecular ions. So here's an example of a detection of this linear C3H+, which, as you can see, plays a very central role to this carbon chemistry in regions like photodissociation regions. And this detection really helps, pin down these models and understand the type of chemistry that is happening. However, for more complex molecules, it really requires, or it really is helpful to have laboratory data to guide the observations, or even in this case, laboratory data was needed to confirm the carrier of this transition. And so how to actually obtain these rotational transitions in the laboratory. So here we have, let's just say, a simple molecule. So here are the different rotational energy levels, and you can try to observe the transitions between them. Now, this has been done, for a long time in laboratory experiments, but for ions, it can be very challenging. So when you generate them, they're generated in very small abundances. There's usually a lot of interfering species that are at much higher concentrations. And so to try and measure these with pure rotational spectroscopy can be quite tedious because it requires a lot of averaging and slow searching. And so what I have done for my work during my PhD, so here's an example of a molecular ion, HEH+. And so here are the rotational transitions, and these are separated by hundreds of wave numbers. So these are very spread out for these light molecules, meaning that to also cover all these transitions would take many different experimental setups, taking just an unreasonable amount of time. And so the work I did was using indirect rotational spectroscopy using the vibrational structure. So here we have, let's say, another molecule with these vibrational energy levels. And so you have these strong fundamental band transitions in the infrared. And then if we zoom in, these vibrational levels are composed of this rotational fine structure. And so if you observe these transitions in high resolution, you can recover the rotational structure using infrared measurements. So here we can see another simulation of HEH+, and now you have this rotational structure that you can now use to back out the pure rotational transitions, which you can do by either taking the differences between different transitions or by fitting these to an effective Hamiltonian. But it's not all great. You do have the issue of now you are contending with Doppler broadening. So at higher frequencies, the Doppler widths of these are going to be much larger. So here is just an example of a measurement of methane, but now these are on the order of hundreds of megahertz, the widths of these transitions, meaning so for one, it lowers the ability, how well you can determine these transitions, where for astronomy, you really want to be able to know the exact frequency to within a megahertz or better. And also you lose resolution as far as trying to detect finer structure in things. And so I have used a couple different approaches to try and contend with this Doppler broadening. So for one, it's using velocity modulation techniques. And so this was the workhorse for decades in ion spectroscopy, where you generate your ions in an AC discharge. And because the electric field inside this tube is oscillating back and forth, your ions will be drifting back and forth, causing the Doppler profile to shift back and forth. And then you can detect this by demodulating at that modulation frequency, meaning that you only detect ions and not the other neutrals present. So here's the first example of a velocity modulation detection of HN2+. But this is still Doppler broadened. So to get past this, we added a cavity around this cell. So now the light will pass many times through the sample, which improves your sensitivity, but also will generate this smaller feature at the center of your transitions. So now this is only about 70 megahertz wide instead of hundreds of megahertz. This is for a measurement we did of H3+. And so now you can determine these transitions quite accurately. One limitation with these types of experiments is that you really can't get to that low of temperature. So you're really limited to about maybe 170 Kelvin with liquid nitrogen cooling. And so the question is, when you get to larger molecules, they become harder and harder to detect. And so another method that I used in the collaboration or in working with the group in Cologne is action spectroscopy, which Juliana gave a nice introduction to. But now instead of looking at how the molecules absorb the light, so here you're looking at the change in the light, here you're looking at the change in the ions. And so you can select a particular mass that you want to look at, trap it in the example for this type of apparatus, expose it to light, and then you look at changes that the light causes. So for example, you can look at a reaction that occurs, or let's say preventing a cluster from forming. And then you get these nice, very narrow transitions. So this baseline is the number of CH5+ helium clusters formed. And when it comes onto a resonance, the number of clusters drops. And so here you can see a transition of the bare CH5+ ion. And these have very narrow Doppler widths of, again, on the same order of under 100 megahertz. And so you can determine these frequencies rather accurately. And so for the rest of the talk, I'm going to talk about an investigation using an action spectroscopy technique on a molecule that's very important to photodissociation regions. And so in photodissociation regions and much of the interstellar medium, small hydrocarbons are rather ubiquitous. So these small, so for example, we have the linear and cyclic versions of C3H2, which have been observed in a number of environments, diffuse and dense. And so the question is, where are these molecules coming from? Are they fragments from polycyclic aromatic hydrocarbons or larger molecules that were discussed earlier, or are they formed from the bottom up using gas phase reactions? And so here we have this network of carbon chemistry here again. And as you can see, the growth process is really through this addition of C+, which allows for the growth of these molecules. And then to add hydrogens either occurs through this hydrogen abstraction or through radiative association. And then these can be destroyed by recombination with their electrons to form the neutrals that have been observed. And so again, it's very helpful to try and observe these intermediates. So C3H+ has been observed, but we set our sights on C3H2+ as another possible target to try and measure in the laboratory to help with astronomical detection of it. Another reason why we were interested in this molecule is that it did show some unique chemistry. So this process of hydrogen abstraction is important in these environments, as I mentioned. And when the reaction is exothermic, it usually occurs at this barrierless reaction rate, as you can see here. and this being the heat of reaction. However, there's one very clear exception, and that was this reaction between C3H2+ and molecular hydrogen. And so we set out to study this using action spectroscopy, known as laser-induced reactions. And so here what you're doing is through resonant excitation, you are causing a reaction to occur. So if we have this endothermic reaction in a standard configuration, if you vibrationally excite the ion, these can now actually react to form the products. And so what you see is this nice background-free detection of these rho vibrational or whatever type of transition you are probing. However, our scheme is a little bit different here because we're not looking at an endothermic reaction, but an exothermic reaction that just occurs very slowly. And it was thought to have a small barrier because it has a negative temperature dependence at very low temperature. And again, it occurs very slowly. And so what happens when you vibrationally excite the ions, which we were thinking maybe it will help get you over this barrier. And so we did this using the Coltrap apparatus in Cologne, looking for this new 7 CH asymmetric stretch, so this mode, which had been detected in low resolution at the Felix light source. And so the C3H2+ ions were selected and held in the trap, where they collided with hydrogen molecules, and then we irradiated it with narrowband mid-infrared light, and then saw the products that formed after around 400 milliseconds, and began searching around this region. And what we found were these, so here you can see this baseline, which is the product C3H3+ ions forming. And instead of seeing what maybe we expected, which was promotion in the reactivity at certain very narrow frequencies, we saw these depletion features. So we saw these narrow transitions where the number of products forming was decreasing. And this was very reproducible. And by surveying where all these transitions were, we could spectroscopically assign it to this cyclic C3H2+ ion. So we knew it was coming from this ion, but the question was, why was vibrational excitation stopping this reaction from occurring? So high-level quantum chemical calculations were done to try to understand this potential energy surface of this reaction. And so here you can see the results. And what was found is that we found this local minima before the transition state, where the hydrogen molecule sits on this along the line of the CH bond. And so now you can imagine in the ground state, this reactive complex forms. It will often just dissociate back to reactants. Sometimes it can tunnel through this barrier to form the product. But if you were to vibrationally excite it, what you could expect is that you're going to break up this reactive complex, preventing the reaction from occurring. And so this presented a nice mechanism to explain why vibrational excitation, adding energy to the system, could prevent a reaction from occurring. But what it was not able to explain by itself was how large these signals really were. So here we have, again, the background signals, these narrow features. And here you can see the amount of product form was reduced by 15%. And the reason why this is, very interesting is that the state that is being probed by this transition only has about 1% of the total ions. So how does exciting a small fraction of the ions cause such a large depletion in the reactivity? And so to try and understand this, a simple model was constructed of the different processes that are occurring within this experiment. So here we have the ensemble of different rotational states of the ground state ion. And here we have the state that we're probing with our infrared light. So the light is only resonant with this transition with the initial and final state. And in the vibrationally excited state, the ions will not react. And so if you tune to this transition, you will start moving ions to the vibrationally excited state. But as that process is occurring, you're going to start relaxing them through stimulated emission, and they will also be returning through collisional relaxation and spontaneous emission. And so here, you could think that you only have maybe 1% of ions in this state, and you're only really able to excite only a fraction of that. But if you consider another inelastic process, which is rotational relaxation. And so this is a very efficient process. So as these vibrationally excited ions are colliding with the hydrogen gas because they don't often react, but they're very likely to become rotationally thermalized. So now you're going to start moving population from this excited state to other rotational states up here, which will relax down slowly because they're no longer affected by stimulated emission. And so what you get is this funneling of molecules of ions through this transition to the vibrationally excited state. And if you consider the relative rates of these processes, you will quickly be putting a lot of ions in the vibrationally excited state. So here we can see in tens of milliseconds, we expect to get, roughly between 5 and 20% of the ions in this excited state, depending on the background, the pressure. But if you assume that things in the vibrationally excited state can't react, this will cause a significant depletion in your reactivity. And so we use this to perform a spectroscopic survey of this molecule, measuring 91 row vibrational transitions in this band. So you can see the P-gopher simulation versus our experimental data. And we reached up to a rotational level of around of 5. This is also an open shell molecule, so it has this doublet ground state. And so we have spin rotation fine structure, which we could at times resolve, sometimes as an overlapping feature, and sometimes just as a broadened transition. But we were able to fit all these transitions to an effective Hamiltonian to derive rotational constants with the idea that we could use these to predict rotational transition frequencies for radio astronomy. And so we did that. Because the molecule has quite a substantial dipole moment, it should be possible to observe it astronomically or in laboratory measurements. These transition frequencies have uncertainties of more than 5 megahertz, so probably not good enough for a targeted search, but should be sufficient for, let's say, a survey measurement in assigning transitions to this molecule. Unfortunately, we were not able to detect it ourselves with a laboratory search using a different action spectroscopic technique. But again, we were still able to predict them within this 5 to 45 megahertz uncertainty. And so in conclusion, I use this new method of laser-induced hindering of a reaction to study this reaction between cyclic C3H2+ and molecular hydrogen, supporting the mechanism with quantum calculations as well as qualitative modeling of the different photon and inelastic collisions occurring to the molecule, helping us understand this interesting reaction. And it also shows that high resolution row vibrational spectroscopy can still help radio astronomers in predicting these transitions. So I'd like to thank Stefan Schlemmer's group in Cologne, as well as Jürgen Gauss's group for doing the calculations, and my funding sources for this project. And I would like to thank all of you for your time, since we went a little over the hour. Thanks.
Thanks, Charlie. So we have a few questions to close the seminar. We have a question from Bob Phil. It says, it is well established in the folklore that ion neutral reactions are barrierless, but is this true? A few Kelvin barrier could have some relevance in a few Kelvin conditions in ISM.
Yeah, so I guess much of this talk showed that it is a bit of folklore. So it is a sort of a rule of thumb that these reactions, if exothermic, will be barrierless, but especially with hydrogen abstraction from molecular hydrogen, there are many cases where there is a small barrier, which means that at low temperature, things can get interesting. So at times, tunneling can increase the rate at low temperature through these barriers, but again, you can't just assume that it's happening at the collisional rate for many of these systems.
Cool. And there's a question from Jinju Liu. For a cavity-enhanced velocity modulation spectroscopy, basically, they're asking about how this cavity is being set up, like in a little bit more detail. It's finest, but I guess it's more like
Yeah, so sorry, I didn't focus on it due to time, but yeah, the way that was set up was actually using windows to contain the plasma. So using Brewster angled windows, which allows for high transmission, and then the cavity was set up around that. So you have a discharge cell with windows and then a cavity. You don't get quite the cavity enhancement as when you have windows directly on there because you have losses on those windows, but we were able to make it work well enough for the purpose of cavity enhanced spectroscopy there. And
Well, all right. And so for the last question, so about your calculation for the potential energy surface, did you find that multi-reference effects are important for the C3H2 plus?
So I would have to refer to so Jürgen Gauss and Philippot did these calculations. I am not sure if multi-reference geometry had a significant effect with the hydrogen. I know they just searched for these critical points and confirmed that they were minima, but I'm not aware if that was this. So sorry, I can't speak on that. I was more involved in the experimental side.